5.2 video lecture. I'm your instructor, Dr. Scott Spaniel, here once again to talk about statistics. So in this section today, we're going to delve into some of the rules that we use when it comes to trying to find the probability of compound events. So these are events that where more than one thing tends to be happening. So today we're going to talk about the addition rule, and we're going to talk about complements. So go ahead and take out your note sheets, which you can find in Blackboard or on MyMathLab, depending on your course format. And we'll get started on page 8 in the Chapter 5 handouts. So, two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive. Okay, now we can use Venn diagrams to look at what probability events look like. So if this is rectangle represents my entire sample space, then I can draw a circle to represent event E, and I can draw a circle to represent event F. And notice if they're disjoint, they have no outcomes in common. So if you knew the probability of each of these, the easiest way to find the total would just be to put them together, right? To add them together. So the probability of for two mutually exclusive events, when you want to do one or the other, is the probability of E plus the probability of F. So if they don't have anything in common, you can simply add their probabilities together. So an example that would involve mutually exclusive or disjoint events is one where you have the number of rooms in U.S. housing units. Okay, so you can't have a house that has both 7 and 8 rooms, right? You have to have one or the other. So these would be mutually exclusive. You can't fall into more than one category, with the exception of 8 or more, but we're just grouping that all together as one category. So the first thing it asks you to do here is verify that this is a probability model. So we have to remember what that means from the last section. So there are two things that have to happen to be a probability model. One is all your probabilities have to be between 0 and 1. So of all the outcomes. So our 0 is less than or equal to P of E. Let's use lowercase e for that. P of E, which is less than or equal to 1. So for all those, that works. So that's true. And then the other thing is the sum of all the P sub E's has to equal 1. And we could check that, but it does work here. So I'm just going to skip over that part. So those are the two things that have to happen. And when you are adding them together, you can be off by a slight. Like you could get, in this case, like 0.999 would be fine, or 0.001 because of rounding. This might not get exactly 1, but you have to be really, really close to 1. So now we can start using this because it's a probability model. So what is the probability that a randomly selected housing unit has 4 or more rooms? Okay, so 4 or more rooms here would just mean what is the probability of 4 or 5 or 6 or 7 or 8 or more rooms. Okay, and so to do that, we can simply add those together, right? The probability of 4 plus the probability of 5 plus the probability of 6 plus the probability of 7 plus the probability of 8 or more. Because those are mutually exclusive events. So we can simply add their probabilities together. So that would just be 0.00, I'm reading from the top of the list. I need to start with 4. So that would be 0.183 plus 0.230 plus 0.204 plus 0.123 plus 0.156. And so when we plug that in our calculator, we get 0.896. Okay, so that's the idea there. So what is the probability that a randomly selected housing unit has fewer than 8 rooms? Well, let's actually, so one of the ways to do fewer than 8 rooms would be simply to add all of these together, right? But there's something we want to remember, which is that we know the total probability of this thing is 1. So another way to do this, if I want to do the probability of less than 8, I could instead do 1 minus the probability of 8 or more. Right? We haven't said you could necessarily do that, but that should make sense, right? Because you could take the total probability minus the probabilities you already know. So I could do 1 minus 0.156 and get 0.844. And if you did add up all the ones I listed, you would get that exact same answer. So what is the probability that a housing unit has 4 to 6 rooms inclusive? So first of all, the word inclusive means we're including the 2 endpoints. With this, it means the probability of 4 or 5 or 6. But if I didn't have that word inclusive, it would not include 4 or 6. So it would just mean the probability of 5. And so those are mutually exclusive. So just like we did up above, we can do the probability of 4 plus the probability of 5 plus the probability of 6. Okay, so that would be 0.183 plus 0.2030 plus 0.204. And so when we do that, we get 0.613. Okay, and so that's the idea of using this addition rule for disjoint events. This last one, though, gets back into this idea from this problem here, which is, what is the probability that a randomly selected housing unit has at least 2 rooms? Well, the word at least 2 means 2 or more. So that would be all of these. So we could use the same idea as before. We could add all of these numbers up, this one, add those all together to answer this question. Or we could realize that that is everything except for 1. So to do the probability of at least 2, we could instead do 1 minus the probability of 1. So that'd be 1 minus 0.005, which is 0.995. Okay. And this problem, these 2 problems where I did 1 minus, lead us into these definitions at the bottom of the page. So let S denote the sample space of a probability experiment and let E denote an event. The complement of E, which we write E with a little subscript, an exponent C, is all the outcomes in the sample space that are not outcomes of event E. So if this is my Venn diagram, here's my sample space. Inside the circle is E. Then all of this out here is E complement, the complement of E. So to find the complement of E, we do exactly what we did in this problem here. We do 1 minus the probability of E. Okay, so in a lot of cases, when you want to find the probability of a lot of outcomes happening, like at least 2, it may be a lot easier to take 1 minus the probability of its complement. Okay, so that's what we're looking at there. So what I'd like y'all to do is take a few minutes, pause the video, and try this problem. Okay, so go ahead and do that now. Okay. So now that you guys have tried, let's go through the answers here. So you should have first showed that this was a probability model. So was every probability less than, greater than or equal to 0 and less than or equal to 1? Yes. So that works. And if you add these all up, do you get approximately 1? Yes. So that is a probability model. So what is the probability that a randomly selected doctoral candidate who earned a degree in 2005 studied physical science or life science? Okay, so we just add those 2 together. So the probability of physical or life science is just 0.100 plus 0.171, which is 0.271. Okay. What is the probability that a randomly selected doctoral student earned a degree in 2005, studied physical science, life science, mathematics, or computer science? These are all mutually exclusive again, so we're just going to add those 4 together. So that's 0.325. Okay. What is the probability that a randomly selected doctoral student earned a degree in 2005 did not study mathematics? So that would be the complement of this, right? So that would be everything else. So we can, to find they did not, we can just take 1 minus the probability that they did study math. So that would be 1 minus 0.028. Yep. So that's 0.972. Are doctoral degrees in mathematics unusual? Yes. Okay, 0.028 is less than 0.05, so they are unusual. And then I'll let you answer that last part on your own. Do you think that is surprising? Okay. So that is mutually exclusive events. So that means if events overlap at all, we cannot use this. Instead, we need to use what's called the general addition rule. So let's look at the general addition rule. So let's assume, here's our sample space, S. We have 2 events. If we don't know anything about them, we have to assume they overlap. Okay? Something like that. And so the problem is, if we add the probability of E plus the probability of F, well, I'll give you a second to think about it. What's the problem here? Well, the problem is this part in the middle, which is E and F, gets counted twice. It got counted once as E and once as F. So it got counted twice. We only want to count it once, so what we have to do is subtract it away once. And so now it got subtracted away, and now we're okay. Okay? So that's how you're going to do these things in general, is you can do them just like the disjoint one. You just have to get rid of any overlap. And if there is no overlap, then that's not going to be a problem. Okay? So let's look at some examples that go along with this. So the following data represent the number of drivers in fatal crashes in the United States in 2005 by age group for male and female drivers. So determine the probability that a randomly selected driver involved in a fatal crash was male. Okay, so what we want to do is, the probability of male, right, is the number of males divided by the number in the whole sample space, the total. So that'd be 42,949 divided by 57,909. So that's 0.742. Determine the probability that the randomly selected driver in a fatal crash was 16 to 20 years old. So the probability of 16 to 20 is the number of 16 to 20-year-olds divided by the total number in the sample space. So 16 to 20's total is 7,293 divided by the total, which is 57909. Which is 0.126. So then it says, determine the probability that a randomly selected driver in a fatal crash was 16 to 20-year-old male. So the probability of a 16 to 20-year-old male is the number of 16 to 20-year-old males divided by the total number in the sample space. So 16 to 20-year-old males is 5,180 divided by 57,909. So that's 0.089. And so now, if I want to determine the probability that a randomly selected driver involved in a fatal crash was male or 16 to 20 years old, so the probability of 16 to 20 or male, I would want to add the probability of male plus the probability of 16 to 20. And then the problem is these guys here got counted twice, right? They get counted as male and they get counted as 16 to 20. So what I would need to do is I would need to subtract away that probability of 16 to 20-year-old male. So that would be 0.742 plus 0.126 minus 0.089. So that's 0.779. Now, I didn't necessarily have to do it that way. I could instead, and I'll write this up here at the top, I could have done 42,949 plus 7,293 minus 5,180 divided by 57909. So because they all have the same denominator, you could add and then subtract the quantities and then do the division rather than finding the probabilities and then adding and subtracting. Either of those work. They give exactly the same answer, but those are two different ways to look at it. And then the last question here doesn't necessarily have to do with the or rule, but it's just a question they want us to answer. So would it be unusual for a randomly selected driver involved in a fatal crash to be a 16 to 20-year-old female? So that's just the probability of 16 to 20-year-old female is the number of 16 to 20-year-old females divided by the total number of drivers. So that's 16 to 20-year-old females is 2,113 divided by 57909. And when you do that, you get 0.0364, which is less than 0.05. So yes, it is unusual. Okay, so that's the idea of how to use the general addition rule. So what I'd like y'all to do now is flip over to page 11 and try doing these problems that involve the general addition rule. Okay, so now that you've all tried this, let's try this together. So if a survey participant is selected at random, what is the probability that he or she is satisfied with the student government? So satisfied is 231 out of a total of 357. So 231 divided by 357 is 0.616. What is the probability that he or she is a junior? So juniors are 94 out of 375. Which is 0.251. And then what is the probability that he or she is satisfied and a junior? So satisfied juniors is 64 out of 375, which is 0.171. And then what is the probability that he or she is satisfied or a junior? So you could add and subtract the answers we already found, or you could add and subtract these things, satisfied or a junior. So we could do satisfied, 231, plus a junior, and then we just have to realize we have to subtract if there's any overlap. Whoops, I wrote the wrong number here. So 94 minus the 64 that are overlap over 375. So that's 261 divided by 375. Which is 0.696. Which okay, so that's the idea there. Okay, and then for the second one, the only thing that's slightly different here is they didn't tell you the totals. So you need to figure out the totals here. So this would be 17.4 million, and then 2.4 million, which is 19.8 million total. And then the total for female would be 10.5 million. The total for male would be 11.3 million, which also adds up to, whoops, I did something wrong. Yep, this should be, I screwed up a couple of these. So this should be 19.4, and so yeah, this should be 21.8. And that's a good example of why it's a good idea to check both directions to make sure you get the same answer here. Okay, and then the rest of this problem is just like the one we just did. So what is the probability that a 16 to 24-year-old individual from the labor force is employed? So you take total for employed divided by the total. What is the probability that randomly selected 16 to 24-year-old individual from the civilian labor force is male? So you take the total for male divided by the total. Then what is the probability that they're both? So you take the total for male and employed and then you can add and subtract. So it'd be 19.4 plus 11.3 minus 9.9 over 21.8. So 20.8 divided by 21.8 is 0.954. Okay. Now, the last thing I want to talk about in this section isn't necessarily a new technique or anything like that. It's simply that one of the types of problems I tend to do a lot in this textbook and in probability in general has to do with playing cards. Because playing cards are an example of equally likely outcomes that really fit. So I don't want to assume that everybody knows enough about a deck of cards in order to answer questions about it. So that's why I've listed this here. So decks of cards are broken up into 4 suits. Okay, so we've got the suits, which are spades, which you can kind of see from the picture, but I'll try to draw a better one here. No, that's not bad. Hearts, clubs, and diamonds. Okay, each suit has 13 colors in it. They're also broken up, 13 cards in them. They're also broken up into 2 colors. Okay, so the hearts and diamonds are red, as you can see in the picture. Spades and clubs are black. Okay. And then you've got the card. So the single card is called the ace, which is why it's got an A on it. But then we've got 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then we've got the J, Q, and K, which are the jack, the queen, and the king. And these cards are called face cards because they have faces on them. Okay? And so I think that's enough information about playing cards for you to be able to do any of these probability problems. So compute the probability that a randomly selected card is a heart or a club. So these are all mutually exclusive. So the first question, so how many hearts are there? Well, there's 13 each suit out of 52 total. And then how many clubs are there? Well, there's 13 out of 52. You could also say that because there are the same number of hearts and clubs, you could say that hearts are 1 out of 4 suits and clubs are 1 out of 4 suits. Either way you do this problem, you get 1/2 as the final answer. Notice I didn't do any subtracting because is there any overlap between hearts and clubs? No, there's no card or cards that are in both. So then we could compute the probability that a randomly selected card is a heart, a club, or a diamond. Well, hearts, clubs, and diamonds are all mutually exclusive, so I can just take 1 out of 4 for hearts, 1 out of 4 for clubs, and 1 out of 4 for diamonds, and we get a probability of 3/4. Then it says, compute the probability that a randomly selected card is an ace or a heart. The problem here is these are not mutually exclusive because there is a card that is both an ace and a heart, the ace of hearts. So we can do the probability that an ace is selected. So that's 1 out of 13. There are 13 types of cards. Ace is one of them. We can take plus the probability that a heart is selected, which is 1 out of 4, and then subtract the probability that it's the ace of hearts, which is 1 out of 52. You could also do this as 4 aces out of 52 cards, plus 13 hearts out of 52 cards, minus 1 ace of hearts out of 52 cards. And either way, you get 16 out of 52, which is 4/13. Okay? So at this point, why don't you all pause the video and try these last 3 problems. And then we'll go over them, and then we'll be done with this section. Okay, so now that you've had a chance to try them, let's go through these together. So compute the probability that a randomly selected card is a 2 or a 3. So the probability that a card is a 2 is 4 out of 52, or and the possibility that it's a 3 is also 4 out of 52. You could also say the probability that a card is a 2 is 1 out of 13. Same goes for 3. Add those together and you get 2 out of 13. And you don't have to worry about subtracting because there are no cards that are both. Okay? If we did it for 2, 3, or 4, they're still mutually exclusive, so I just have to add the probability of a 4 into the previous problem, which would give me 3 out of 13. And then last but not least, what is the probability that a card is a 2 or a club? Okay, so that's actually going to be almost identical to this problem we did up here because there's not really that much different in doing an ace or a heart as a 2 or a club. But the probability that a card is a 2 is 4 out of 52. The probability that a card is a club is 13 out of 52. And the probability that it's a 2 of clubs is 1 out of 52. So that's 16 out of 52, which is 4/13. Okay. So that is it for this section. If you have any questions, like always, feel free to contact me through email or remind. And don't forget to do your homework and quizzes and tests and come to class or do the discussions. I'll see you next time.